Isothermal process. You decrease the volume, you increase the pressure. You increase the volume, you decrease the pressure. You could measure volume and the pressure and derive the law which relates these variables when temperature is constant, and turns out pressure and volume inversely proportional in such a way so product remains constant. And this is one more neat demonstration device which is a model of of cooling down and warming up. And you could see that light, small particles move faster, and large, heavy one clearly move slower. And we know why. Because they shouldn't be moving equally fast. They should have the same kinetic energy on average. So mv squared over 2 should be the same, or close. So when mass increases, they should travel slower. When mass decreases, they should travel faster. And if we, in this model, turn the temperature down to 0, they don't move anymore. So again, found in the resource room from old Mac. So probably one of yours. And we've learned almost everything. So we're going to solve problems today very soon. Now, a couple of more conceptual remarks. How can we change the internal energy? For example, we can heat it up, like in this experiment. If temperature rises, molecule starts moving faster. But we also can do some work. For example, if you ride a bicycle, if you need to pump air in a tire, if you do it again and again, you feel it becomes warmer. Warmer means higher temperature. Higher temperature means kinetic energy, average kinetic energy of air inside rises. And clearly we know why, because if you move a piston quickly, every time when it collides with molecules or atoms, it makes them move faster. It's a collision. It's like hitting a ball with a racket. So these are two options we can use if we want to change the internal energy, heating up or doing work on a system, or both. But we don't write this equation like that, because this is a work of outside, from outside. We use the Newton's third law, and we say that the work done by forces on the system has the same magnitude, but opposite to the work done by the system on those objects outside of it. So this is how we rewrite this equation. And this equation has a name, the first law of thermodynamics. There is a 0th, there is a second, but this is the first law of thermodynamics. And how we read it? We read it that if a system, well, this is one of the examples. If a system absorbs heat, it can spend it differently, either by changing the internal energy or by doing the work. For example, same device, same hot water, And you know what's going to happen. Now here we have no any moving object. It's only due to heat transfer from hot water to the air inside this plastic can. But what does it do? It lifts. That's a mechanical motion. There is displacement, force, there is work done. We can actually calculate the amount of work and, relate heat and mechanical work. There is a so-called mechanical equivalent of heat, was measured by Professor Joule. So of course, now we need to say something about how do we calculate work. And we know for a constant force, when the force is constant, work equals force times displacement times cosine of the angle. Well, if force divided by area, that gives pressure. So we can just rewrite the same equation in terms of pressure and change of the volume of a system. This, of course, only works for the constant force, which means for the constant pressure. Like in that experiment, the pressure remains constant. And that is what we call isobaric process. And the graph for the isobaric process is this straight line. The volume changes, but the pressure remains the same, P, 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 P. And if we multiply two numbers, the pressure, which on this graph is represented by, well, this number, and the change in the volume, that's what we get. The area of this rectangle. But of course, we can make a generalization, a transition. If the pressure changes, we always can break it down into smaller processes. For each processes, we can calculate the area, which will represent the tiny work done during that particular process, add them up. So turns out we can always calculate the work done by a system by calculating the area on this graph, the pressure as a function of the volume. So when the volume increases, like in this experiment, the system expands, it pushes on the objects around. So gas does positive work. Otherwise, if we compress the gas, we do positive work. So when the volume decreases, the work done by gas, by the system, is negative. That's it. That's all we need to keep in mind. If we use this equation, pressure times change in the volume, it takes taken care of automatically. Yeah. If we increase the volume, so this difference is positive. If we decrease the volume, this difference is negative. Here, if we use the area, we need to remember that sometimes we have to choose a plus when the volume increases, and when the volume decreases, we should choose a minus for this area. And when the volume doesn't change, there is no work, no matter what is happening. It might be getting hotter and hotter and hotter, but if the volume is constant, there is no work done. Mechanical work, that's what we call it, mechanical work. Yes?
So is this true for all the types of chapter or just for the isobaric?
You should be more specific which equation. We have two, this or that. This?
PV2 minus V1.
This one?
Yeah.
See? Only for the isobaric. If it's not isobaric, we gotta use this. There is always average pressure. If pressure changes, there is always the average pressure. And if we know that average pressure, we can apply this equation as well. It still will be equal to the total area. Of course, we will not need to use this approach for some complicated graphs. As long as it's a straight line, we know what to do. For any linear graph, we always can calculate the area. It could have been a triangle or trapezoid, you know, that's it. So this is the summary of everything we've said on one slide, probably. Could have been using this just 2 weeks ago or 2 days ago. But I don't like an approach some people like when they, like a rabbit from a hat, say, this is the equation. What does it mean? Who knows? Who cares? Let's just use it. That's not my approach. So let's do the problem. Here we have 3 different processes done on the same system. It doesn't matter how many processes, 1, 2, 3, 4, 5. The approach will be the same. So this question is about this process. From this state, high pressure, high volume, to this state, lower pressure, lower volume. So this is how we change it. How can we do that? Doesn't matter. We can do it by our hand. Yes? Oh, yes. Well, you know, of course, now it's not. It happens when you copy and paste, and forget to change something. So the work is a number. As any number, it can be only negative, 0, positive. That's your choice, right? So, and normally I would, again, draw a graph just for that process I want to investigate. All other processes don't matter here. State number 2, state number 3. We could call it initial and final. A and B, doesn't matter. That's supposed to be, for this particular process, the initial volume. That's supposed to be the final volume. Well, technically, that's supposed to be the initial pressure, and that's supposed to be the final pressure. Now, I don't want to restore you. No, slideshow. All right. Now, does pressure change or is it constant? The pressure changes. It's not constant. For that process, 1 to 2, the pressure doesn't change. For process 3 to 1, the pressure changes, but the volume stays the same. And in this process, they both change. The volume changes, the pressure changes. So can I use this equation? Work 2 to 3 is equal to P times delta V. No, I can't, unless I fix it like this. For example, I can calculate the average. And I could have done that because the average will be just in between right here, 1/2 between those two. But here we just need to choose between being negative, being 0, and being positive. And the clue is what is happening to the volume. Does the volume change? Yes. How? How do we call this change? Decrease. A decrease. So when the volume is decreasing, the work is negative. That's it. That's what we need to remember. So in this situation, you had two correct answers initially. Well, and now we just need to calculate that work. So this is a standard set of equations. On equation sheet you have more, but these are more important because we're going to use mostly these ones. And of course, what should we use to calculate something? For example, if we're calculating work, we have two equations related to this variable. So that's a fork. If we know what to do, we do it. That's not a problem. That's a task. The problem is when we don't know what to do, like which equation should we start using. In that situation, what do we do? Just try one, just guess. Trial and error. But of course, if you try it again and again and again, you have an experience which tells you, like clues. In this situation, the volume and pressure changes, so probably we should use something related to the volume and the change, and that is this equation. So all we need to do is just calculate the area. Area of what? Well, again, it is helpful to draw just that single line which represents that single process. Now, what do we know about these two states? Do we know this volume? We need this number, so we have to say something about it. What do you think? Exactly. So this process is happening at constant volume. That's what we should call V1. But since the process happening with no change, that is V1, and that is 40 liters. What else do we know about this state? Pressure. We know the pressure, 200 kilopascals. All right. For this state, what do we know? This volume is just given to us, 120 liters, and this pressure, P2. Do we know this pressure? What do you think? We need this number, so we have to say something about it. What do you think? It is equal to P1. We've mentioned that this process is happening at constant pressure. So that should be 600 kilopascals. And this, how we use graphs, not just this one. We read them to extract information about different parameters which might be equal to each other. Now, well, if we're calculating area, the area of this thing we need to calculate. A trapezoid. So, what equation should I write? And the area represents the magnitude of this work. As we said, it has to be negative. So the final number will be equal to work during this process should be equal to -1 times the magnitude of whatever we get. So how do we calculate this area? There are two approaches people use. You can break it down in two parts, a triangle and a rectangle. Or you can kind of, in your mind, turn it by 90 degrees. It will look like a standard trapezoid. And for a standard trapezoid, you can use a standard equation for the area. So, well, I use the equation for the trapezoid. So it should be 1/2 times, well, in algebraical, it should be P2 plus P3, two bases. If we turn it times delta V. That's what it is. Which again agrees with this calculation. Because the average pressure for the linear graph is just initial plus final over 2. Now, so in numbers, 1/2 600 kilo pascals plus 200 kilo pascals times change in the volume well, I'm calculating magnitude, so it's going to be 120 liters minus 40 liters. Now I want to point at the interesting fact again. If we use liters, kilos, kilo, a plus. I said kilo plus. Yeah. I said kilo, and I already was thinking about liters. So these powers of 10 getting canceled. So as we have 1/2 times 800 times 80. Yes? I did. That's what I said. Liter, and I wrote 10 to the negative third. I didn't write 120. Yes, I wrote 120 times 10 to the negative third. So that's exactly what I did. So this is 600 times 10 to the third pascals. This is 200 times 10 to the third pascal. This is 40 times 10 to the negative third cubic meters. This is 120 times 10 to the negative third cubic meters. So basically, kilopascal times a liter equals Pascal times a cubic meter, which is a joule. All right. So, any questions? Well, what else can we calculate? Lots of things. First of all, we have more processes, plus for each process, in addition to work, we know that temperature might change, energy might change, so a system might absorb or release some amount of heat. So in this situation, what I try to do is first just write everything I can about pressure, volume, temperature if I can, for each state involved in what's happening. So pressure, P1, 600 kilopascals, bless you. Volume, V1, I just copy 40 liters. Temperature, not given. Okay, we'll find it. P2 is equal to P1, 600 kilopascals. V2 is equal to 120. Temperature, gotta find it. P3, 200 kilopascals. V3 is the same as V1, 40 liters temperature. Okay, so we need to calculate temperatures now. What equation should we use if we want to relate the temperature, pressure, and volume? Naturally, it's not this or not that. It should be, well, our first guess should be ideal gas law. PV equals nRT. Temperature equals PV over nR. So, in this situation, what temperature is equal to? PV 600 times 40. And we know that kilo and liter cancel each other, divided by this number, 300. This number is given just for convenience. We can calculate the number of moles N if we want to. It will be 300 over 8.31. That's it. And the result is 6032. 2 times 4, 80 Kelvin. T2, all right, we just have to use the same equation. Pressure, volume, 300. Now pressure, volume, 300. Now it's something not exact, well, wherever. All right. Now, let's finish this process, 2, 3. We already know the work was equal to, actually that was area, work equals negative 32,000 joules. 2, 3, 2, 3. So negative 32,000 joules. What else can we calculate? Well, oops, what happened? We know P and V. We could use this equation. Or we know temperatures now. We can use this equation. For any equation, we need this number, but because the gas is diatomic, I equals, yes?
On the last slide, it also asked about problems 1, 2.
I'll go to that. So, that will be 0. No, for 1 to 2, it will not be 0. 1, 3 is 0. I just want to calculate everything, including that. So, since it's a diatomic gas, the number of degrees of freedom, this number should be equal to, and that's what we should remember, 5. So now we can apply any equation, but since we know temperatures, I would use this, yes. We don't. We know from yesterday. Well, I know from people who told it to me, and you know from me because I told it to you. That's it. That's how it works. If you have a monatomic gas, to describe its motion in space, how free it is, all you need is x and y, z axis, 3 numbers, 3 coordinates. To describe a diatomic gas, how it's moved. And we neglect possible oscillations that would make things even more complicated. But if it's just mechanical motion, it travels in space, plus it might rotate about 2 independent axes. So 3 plus 2, 5. And for everything else, 3 degrees for the motion of a center of mass, plus 3 independent rotational axes about the center of mass. 3 plus 3, 6. Since it's diatomic, that's what we read, because we can. We just say, for a diatomic gas, it must be equal to 5. That's it. So now, for this very process, the change in the internal energy should be equal to 5/2, this product, times change in the temperature. Change means change. So 5/2, this should be 300. Change is final minus initial, so it's temperature number 3 minus temperature number 2. So that's going to be 5/2 times 300 times temperature 3, 26.6 minus 240. Also negative. So please tell me a number. Because it's just dark here for me. Hard to read. 240 minus 26.6 times 300 times 5 divided by 2. $19.50. Anyone? Negative 160,000 joules. Okay, yeah. Well, now we can calculate the amount of heat which this system exchanges with the surrounding during this process. Delta U plus W okay, that's now the question during this process, is system releasing or absorbing heat? It's releasing. It's negative. And this completes all possible situations, of course. Well, let's do 1, 2. 1, 2. For 1, 2, this is the graph. Bless you. 1, 2, V1, V2. So for this process, this area is equal to the magnitude of the work. But in this situation, the work will be positive because the gas expands. And for this situation, we don't need to calculate any new values for pressure, volume, or temperature. We use the same. It's just the process different. States are the same. State number 1, state number 2, state number 3. But if it's a different process, we have to repeat the calculation using same equations with different values related to different states. So that should be equal to, well, let's say P1 times delta V, and that gives 600 kilopascals times V2 120 minus 40 liters. So 600 times 80 joules. That's the amount of the work done. What? Today's Wednesday, right? Thank you. You reminded me. I keep forgetting things. I'm getting older. You're young, bright, energetic. I'm in my decline, so you'll learn. Now, what else can we calculate? Delta U. Delta U equals I over 2 nR delta T. When we know temperatures, that's the fastest way to do it. So again, that will be equal to 5 over 2, 300. And here people sometimes get confused. Well, this is the process which begins at state 1, ends at state 2. And change is final minus initial, so it should be T2 minus T1. So 5 over 2, 300 times, looking back, T2, 240, to T1, 80. All right, I need a number. Joules. And now we can apply the first law of thermodynamics to calculate Q. That's going to be 120 plus 48, 168. During this process, what is happening to heat? Is it being absorbed or released? Does system absorb the heat or releases it? Q is positive, absorbs. See, everything is so absorbs. Everything is very clear when we know the rules. This is only for this process. For the process 1 to 2, 1 to 2, 1 to 2. Well, then change 1 to 2, 1 to 2. All right, let's do the last one quickly. First of all, work is equal to what number? 0. There is no change in the volume. Well, delta V31 equals 0, which means that heat will be equal to the change in the internal energy, which will be equal to, again, 5 over 2 nR delta T for this particular process, which begins at state 3, ends at state 1, and now in numbers, 5 over 2, 300, temperature number 1, so it's T1 minus T3, final minus initial, 1, 80. And initial was 26.6. Now we take a calculator and calculate it. Any questions? Yes. No, that's a good question, but let's, this is U. If you want to calculate delta U, you have to calculate U1 minus U3, which means you have to calculate I over 2 P1 V1 minus I over 2 P3 V3. So, what do these terms have in common as a common factor? I, 2, and the volume is the same. You can call it first, you can call it third, but the pressure changes. And we had a similar equation. It's been written in a short way like this. Delta V delta P. But this equation only works when the volume is constant for the isobaric process. And here again you have a time-saving action. You can do it every time like this, deriving this again and again. Or you can just remember for the isobaric process, this is how we can calculate it if we want to. So the work will be zero, but if the volume doesn't change, but pressure changes, temperature must change as well. And if temperature changes, the internal energy must change with the temperature. And already we found everything, so we can just move on to the next problem. Now we have a gas in I don't know, in a balloon or something. Monatomic, what does it mean? What do we say? This word? Yes? We extract that information from reading this text. Monatomic means we have to use I equals 3 if we need it. Maybe we don't need it. It depends on the questions. So, it's your turn now. It's your turn now to select an equation you want to try. There is no guarantee it will work. If it will work, it will give you the answer immediately. However, if it will not work, nothing bad happened. You just have to try something else. Where are the clues? The clues are in the parameters we want to relate. What do we want to relate? We want to relate pressure, volume, and temperature for the state number 1. This relationship, as any other relationship in physics, is given by a specific mathematical expression. So you search and you find the one which you think gives the answer as fast as possible. Then you use your numbers. Then you use your calculator. Oops. Well, I believe you can remember the pattern. If you get 100, press 1, well, select 1, 200, 2, 300, 3. This is the question number 3. P, V, T, these variables. So what equation do you suggest should we use? That would have been my guess as well. It is a guess yet. Until we solve the problem, we don't know if our guess is correct. But this is the most natural guess, or a hypothesis. So T equals, did you choose? What did you choose? What answer did you choose? 1. Okay. Because I didn't see you were doing anything. Well, I mean, did you enter? Because you might choose the answer, but don't enter it. You have to enter. Okay. So we need to apply this equation to the state number 1. 20 kilopascals, 100 liters divided by convenient number. And as we know, kilos and liters cancel each other. So we have, and 20, we have a green here. 20 and 20 cancels each other. So what's left is 100 Kelvin. Kelvin can't wait. $100. Second question for the same situation. Now we are adding some heat. Added. we are adding the heat to the system, means the system is absorbing that heat from us. And the gas expands at constant pressure. That's very important. Every single word gives some information. And of course, eventually it reaches the new equilibrium state. And the question is, what is that temperature equal to? What do you say? Again, I didn't put in equations like F equals ma or torque equals rotational inertia times the angular acceleration. I could have. They exist. But why didn't I add those equations to the list of these equations? What do you think? Hmm? You know, the number of equations in physics is hundreds. And we've learned many of them. But I suggest to look at these. And I don't suggest to look at what we've learned in mechanics. For example, an equation for the elongation of a spring. Why didn't I add that equation to this list? What do you think? Why? It's easier to use these ones.
Variables in them.
We don't have a spring in this equation. So.
Because this situation has nothing to do to any springs. It's like if you want to go to New York, why would you drive to Los Angeles? That wouldn't make any sense. So you confine this set of equations, which makes sense to apply to this particular situation. This is about gas, it's not about spring. So, survey says it's time to see the numbers. Question 4. I need summary. I would do exactly the same. The equation number 2 has nothing really used for us. So, well, which equations do you think, or equations, should we use, at least at the beginning, to relate? What do we need to relate now? We need to relate the amount of heat and eventually the temperature. On this list, do you see any equation which directly relates heat and temperature? No. How many equations do you see for heat? 1. That means that's our natural starting point. The first law of thermodynamics. Because this number, we know this number, it's given number, 2500 should be equal to this plus this. So now the question is, if we still need to make that connection, that means now we have to relate work and change in the internal energy with the temperature. We know how to do that. We've done it before in slightly different situations, but we've done it before here, for example. Delta U equals, etc., etc., etc. So we can start from delta U, right? Oops. Okay, let's just write it. Q equals delta U plus W. This is 2500. Delta U, as we know, and this is the equation I want to use, because my goal is to relate it to temperature. 3 divided by 2 times, well, let's write it as an equation now. 3 divided by 2 times 20 times delta t. What is delta t? Delta t is this difference. This is what we're looking for. This is what we know already. Temperature number 1 equals what? 100. We just found it. So this is technically what we need to find. How much change in temperature happened? Then we take 100, add the change, done. And, well, these are our knowns. 2 unknowns, 1 equation, which means we are not done yet. We got to move on. Well, we have one more variable, W. W is equal to, and now it's important what kind of a process is happening. For the process, at constant pressure, work equals P times delta V, which is equal to P times V2 minus V1, which is equal to P times V2 minus P times V1. Which P? Is it 1? Is it 2? Who cares? It's the same. So this is how I can write it. Any questions on this part? Now, what is product pressure and volume equal to? This is what it is equal to. So it will be equal to this minus this, or we can write it back as this. This is also worth to remember. For the process with constant pressure, in addition to the equation P delta V, we always can use an equation nR delta T, only when pressure remains constant. Still, we have 2 unknowns. Well, this is 20 times delta T. But now we can combine all these 3 equations together. 2500 should be equal to delta U equals, well, let's write it, delta T. Work is equal to delta T. Delta T is the common factor. So now I gotta do it in my mind. 20 over 2, 10, 10 times 3, 30, 30 plus 20 is 50, 50 times delta T. Delta T will be equal to 2500 over 50. 50. This is an example when sometimes we think we have not enough information, but we know what to do. First, we have to believe and just follow the path, and it will lead us to the answers. And of course, now we can calculate that final temperature. 100 plus 50, 150. Any questions? I think it's also very straightforward. As long as we believe in what? In our abilities. Because when people don't believe they can do it, they don't do it. They don't even start. All right, so the calculation and how much work was done. Well, we actually kind of did it already. The work will be equal to 20 times delta T, right? which is 20 times 50, 1,000 joules. Final volume. Well, if we are looking for the final volume, and we already know pressure, which equals to initial, and temperature, which equals to 150, in this situation, the easiest approach, again, using the ideal gas law. I believe I have the answer. Yeah. Any questions? And a homework provides you more chances to practice. The logic is always the same. One more example, probably. I will still have time to do it. Similar to the previous. How do I know? Because I know Q. Which means if I know the amount of heat, Q, I should start from the first law of thermodynamics and see where it will lead me. We know how many moles consist. The pressure is constant, and the volume increases. All right. Delta U, that's what we are looking for. But as we have derived five minutes ago, for the process happening at constant pressure, we can also use this equation, which gives the answer faster because we know the pressure, we know initial volume, we know final volume. And how is it related to do I solve this problem? Yeah, the volume increases. The volume increases, okay. So that's delta U. And that's it, actually. We don't really need Q here in this situation. Oh, no, we do. Energy transfer to a system, 30 moles of an ideal gas, the pressure of this gas constant, and calculate the change in internal energy. It doesn't look like we have any information about I. Maybe it's on purpose, I'm not sure. So at this point, this is what we can say. It should be equal to I over 2 times 2,000 kilopascals times 80 minus 40 liters, and that's it. Okay, so work. Delta V, which will be equal to 2,000 kilopascals times 80 minus 40 liters. Okay, now delta U plus W should be equal to Q. So what does it tell us? I over 2 times 2,000 times 40 plus 2,000 times 40 should be equal to 32,000 joules. Okay, now I see. I guess we can use this equation to figure out what kind of a gas we have by solving it for I. Let's see what, if it's a pure gas, it's going to be 3, 5, or 6. If it's a mixture, it could have been technically anything. If you have a CO2 and hydrogen mixed together, that mixture will not have a given I. It will be some. So what do we have here? Minus 1, 0. All right, so in a case like that, what would I do? How many zeros can I cross out? I have 1, 2, 3, 4 at the bottom, so 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is technically 32 minus 2 times 2 over 8. Why? I forgot this, yeah, this. No, it's going to be 8. Yeah, 32 minus 8 times 2 over 8, 32. So what number? 6. That can be 3, yeah, 6. All right. That's a relief. That means the problem is indeed solvable. All we need to do now, just use this number right here and calculate the change in the internal energy. 6 over 2 times 2000 times 40. It's not 6? I can't do it in my head. 6, 6. 6 times, so 2 and 2 cancel, 6 times 4, 24, and 4 more zeros, joules. Here is a common place when people stop doing anything. They write it and they say, we have no idea what kind of a gas is that, so we cannot solve it. Sometimes we can. We just have to believe and follow the path. All right. You know what? This is exactly the same problem. I can do it tomorrow. And today is the day when you can back at me for everything I did to you. It's the evaluation time. You know what to do. You know what to do because you've done it before many, many times. First of all, I need someone to help to distribute and to collect evaluations. So tomorrow we're gonna finish probably around half of the lecture, and the half of the lecture will be for you Q&A, questions and answers. So prepare your questions. So, would you?
Yeah.
Would you? To help, because it's easier when several people work together. You can distribute. I have extra pencils. And please read the instructions to people. If you need a microphone, you can use my microphone.
No, that's all right.
All right. As you know very well, during the evaluation, I cannot be present, so I'm already not here. But since you really, really wanted slides, I need to spend 5 more minutes to get the slides to the computer. One more reminder, someone left it. And there is something probably yesterday. The Mac power supply for old Mac.